In this chapter, you will learn about the kinetic aspect of chemical reactions. That is the rate, the speed of chemical reactions. The rate of a reaction is the measure of how fast the concentrations of reactants or products change. In the world of chemical reactions, different reactions have rates very different from one another. For example, rusting of an iron nail is a relatively slower reaction than the explosion of natural gas. The study of reaction rates is known as chemical kinetics. You will be learning about the fundamental aspects of chemical kinetics in this chapter. Let's first distinguish between thermodynamics and kinetics, as these two concepts can be easily mixed up. Thermodynamics tells us about the feasibility of a process. That is, will it happen spontaneously or not? And this depends only on the initial and final states. On the other hand, kinetics depends on the intermediate states, and it tells us how fast the reaction will happen, if it will happen determined by thermodynamics. The kinetics aspect depends on the intermediate state because the intermediate state forms a barrier between the reactants and the products. For the conversion to happen, that barrier must be overcome. The height of that barrier is therefore a major factor in the rate of a reaction. The higher the barrier, the slower the reaction will be. And oppositely, the lower the barrier, the faster the reaction will be. The purpose of chemical kinetics is to understand the conditions that affect reaction rates and the molecular events that take place during the reaction to be able to control the rate of the reaction. We want to be able to make a chemical reaction faster or slower according to our needs. With the knowledge of chemical kinetics, we can calculate the time needed for a chemical reaction to reach a desired completion, or the concentration after a known amount of time into the reaction. During a chemical reaction, the reactant molecules collide, resulting in the rearrangement of atoms to form the products. This is the basis of the collision theory. However, not every collision is successful. There are two requirements for a collision to yield the products. The reactant molecules must collide with enough energy, and they must do so with proper orientation. Let's talk about the minimum energy requirement first. This is like a high jumper trying to clear the bar. To clear the bar, the jumper must approach with enough kinetic energy. Otherwise, they will fall short. When it comes to a reaction, the colliding reactants must have a minimum amount of kinetic energy to clear the energy barrier, which is called the activation energy. The magnitude of the activation energy can be shown in a potential energy diagram. The vertical axis shows energy, and the horizontal axis shows the reaction pathway or progress. Reactants are on the left side, and the products are on the right-hand side, separated by the intermediate states. Activation energy is the barrier between the reactants and products. And its value is the difference between the energy of the intermediate state and the energy of the reactants. At this point, we shall discuss the transition state, the highest point in the potential energy diagram. This peak point corresponds to the activated complex, also known as the transition state, and it's an intermediate between the reactants and the products. The activated complex is indicated by the double dagger symbol. The transition state, or the activated complex, is an unstable grouping of all the atoms involved in the reaction. And if the reacting molecules have enough energy, the activated complex can proceed to form the products. A potential energy diagram shows both kinetic and thermodynamic information for both the forward and reverse reactions. Let's look at the forward reaction first. Nitrogen monoxide reacting with chlorine to form nitrosyl chloride and chlorine. The reactants are on the left-hand side, and the products are on the right-hand side. The energy difference between the highest point, called the transition state, and the reactants is the activation energy of the forward reaction. Going forward, this is the barrier that must be overcome. The difference is, for this example, 85 kilojoules per mole. This is the kinetic information we get from the potential energy diagram. Additionally, the energy difference between the products and the reactants, the final and the initial state, corresponds to the enthalpy change of the reaction, positive 83 kilojoules per mole. This is an endothermic reaction. Now, for the reverse reaction, going right to left, the roles are changed. The products are now the reactants, and the reactants are now the products. The reverse reaction has its own activation energy, corresponding to the energy difference between the transition state and the starting point. This is 2 kilojoules per mole. Additionally, the enthalpy change of the reverse reaction is equal to the difference of the final state and the initial state, which corresponds to negative 83 kilojoules per mole, since this reverse reaction is exothermic. The energy difference between the two states is the same, but the direction of the change determines whether the change will be positive or negative. The general look of the potential energy diagram for an exothermic reaction is the same, with one difference. The products are at a lower energy than the reactants. This results in a net decrease in energy, which makes the reaction exothermic in the forward direction. The sign of enthalpy change is negative. Considering the reverse reaction, the energy difference is the same. So the enthalpy change will have the same magnitude, but opposite sign, positive. The reverse reaction is endothermic. The forward and reverse reactions have opposite sign of their delta H values. Activation energy of the forward and the reverse reactions are also indicated on the diagram by the energy difference between the transition state and the starting point, depending on the reaction you're considering, forward or reverse. Activation energy is a factor in the rates of chemical reactions by an inverse relationship. When the activation energy is low, there will be more molecules with enough kinetic energy to overcome the barrier, and the rate of the reaction will be high. Oppositely, when the activation energy is high, there will be fewer molecules with enough energy to overcome the barrier, and the rate of the reaction will be low. Now pause and sketch a potential energy diagram for the reaction of nitrous oxide to produce nitrogen and oxygen, paying attention to the activation energy and the enthalpy change provided.